Welcome to Cover Book Beat. I'm your host, Roger Nichols. If you joined in expecting to see an interview with Charles Liu, the Chinese financier, senior fellow at the Peking University and advisor of the Chinese government, I'm sorry. Somewhere in the multiverse, that universe is happening. On the other hand, if the word quantum causes your eyes to glaze over and your mind to skitter away to other topics, we have the answer for you today. Our Charles Liu, Ph.D., knows what he's talking about. He's professor of astrophysics at the City University of New York's College of Staten Island, an associate with the Hayden Planetarium and Department of Astrophysics at the American Museum of Natural History, and host of the podcast The Liu Universe. He holds degrees in astronomy, astrophysics, and physics from Harvard and the University of Arizona. Currently serves as president of the Astronomical Society of New York, is a fellow of the American Astronomical Society. He does research on colliding galaxies, starburst galaxies, quasars, and star formation history of the universe. In his spare time, Liu also writes for students and general audiences, including the Handy Physics Answer Book, the Handy Astronomy Answer Book, Star Talk with Neil deGrasse Tyson and Jeffrey Lee Simons, and The Cosmos Explained. That's worked out so well, he's been awarded the American Astronomical Society Education Prize and the American Institute of Physics Science Writing Award. His latest book and the subject of our conversation today is the Handy Quantum Physics Answer Book. Very pleased to welcome Dr. Charles Liu.
Hi, thanks so much for having me.
Were you always going to be a scientist?
No, not necessarily. When I was a kid, I had all kinds of loves. I loved writing, I loved music, I loved sports. Over time, I guess as I grew up, I was very lucky that my parents gave me the opportunity to explore and try different things and see what happened. Turns out that I was not that good at sports, despite my efforts, and so that wasn't the best career track for me. And the music stuff and the writing stuff was all part of my life all the way through. But I decided that science was my career, but I still do the music and the writing stuff when I get the chance. So it's all part of my life, and I'm very lucky.
Do you play and write songs?
I have, yes, over time, not whole albums, unfortunately,
Mhm.
because of my time, but yes, uh, mostly uh, playing the piano a little bit for my students or for myself, and singing now, the violin. Those are things that I'm doing, but none of them as professionally as I did when I was younger.
Oh, cool. It's good. Great to get interesting background about that. I really appreciate it because it makes you a real person on top of the excellent scientific thing. So I'm assuming that at some point there was some incident or some key thing that said, I know enough. I'm a good writer. Let's put this together and write for popular people.
Kind of. I guess in my mentality, I always thought that these things were not distinct from doing science.
Mm.
There's a very often a common conception that people have that if you're a scientist, then you must only do scientific research. If you're a writer, then you must only write novels. If you're a musician, then you must only give concerts. But I was lucky enough that I was able to do a little bit of everything. So even as a graduate student, when I was doing my research really concentratedly, I was still singing, performing, and doing little charity concerts for holidays for fun. And my graduate student advisors, my graduate, I guess, faculty advisors and so forth were always a little concerned that maybe I was a little too distracted or a little unfocused or something like that. But they stuck with me also, and I'm very, very fortunate for that. I had great advisors and great professors. And in the end, I think it worked out that I just happened to be the kind of person that I like to do all these things at the same time. And it's enriched me and my science, I believe, as well as all the other things I'm doing with the education and the writing and the
Okay.
fun performing.
Before we leave the performing part, I have to know what sort of music you are involved with. I'm an
Oh,
old disc jockey, so I have to know.
oh, you are. Me too.
Yeah.
Yeah, a little bit of everything. I love all kinds of music. I am a child of the 80s, so a lot of that sort of pop music, rock music of that time is still something that I enjoy. But when I was doing my professional, semi-professional singing and so forth, it was a cappella close harmony. So it was singing jazz, some old-fashioned classical rock and roll a cappella things, and even Renaissance polyphony, classical things like that. So a little bit of everything, and I really enjoyed that. And the same is true when I'm plunking on the piano. I don't pick up the violin as often as I used to, but when I was doing that, that was mostly classical music. The rest of the stuff, it's just whatever popped into my head at the time, and
Well,
whatever everyone's willing to tolerate as I was playing and singing in the room, I guess.
that's fascinating because I've been long a student of a cappella harmony and
Wonderful.
probably have every LOCA, which is the college a cappella annual CD they put out in the competition
Yes.
that's ever been put out. So, yeah,
Wow.
we'll talk
Yes.
later. I'll be in touch. Okay.
Okay. Okay.
Back to the interview. Uh,
Sure.
uh, there, I want us to note that in reading this, it employs some stealth technology. And
Mm.
it's under the guise of a frequently asked questions sheet about quantum physics that managed to smuggle a lot of useful information about the standard model physics in. And you provide a whole bunch of handy mini biographies of important scientists, both famous and those who should be famous. So I want to thank you for that. And this was
Oh,
intentional, I am sure.
well, it's all part of it, right? I mean,
Mhm.
it's maybe stealth on the one hand, but on the other hand, it kind of speaks to how broad quantum physics is and how much it affects us all, even in ways which we may not suspect, right? The standard model of physics, which talks about quarks and bosons and things like that, that happens on the quantum level at size scales much smaller than a millionth of an inch. So when people think of quantum physics who are not specialists, many of them think immediately of those kinds of things. And so there's no reason to exclude them because they are part of the broad umbrella. And
Mhm.
it is, as you said, sort of a way in, right? Some of the biggest, most pressing questions or most common questions are really ways to say really cool stuff about the whole universe. And as far as people are concerned, I really do care about how the story is told. Very often, we're taught in our classwork and so forth that it's a very linear process, that is a very process that doesn't have a lot of life and energy, creativity, and so forth. And when human beings learn science, it's the exact opposite. We're always using creativity. We always have our human energies and our motivations that get into how we ultimately learn about science. And it takes not a day or a month in a laboratory, it takes years, often it takes centuries for an idea to build. And being able to tell that story in its fullness requires biography and requires history. And I'm glad you liked it because that's how I think about science, and that's how I like everybody to think about it as well.
Well, what I particularly like is you taught me some new insights when, and boy, those are more valuable even than the facts as the insights. And one of the ones that, and again, this is peculiar to me, maybe not to anybody else, but I never thought of a cathode ray tube as a first particle accelerator.
Hmm.
It was
Hmm.
great insight. Oh yeah, that clicks. So
Right. Well, I'm glad that's the case. And I'm really glad, Roger, that insights are what you're getting out of this being more important than the facts. I agree with you 100%. Facts are a dime a dozen, right? We can now pretty much get any fact we want with a swipe of a finger or the tap of a mouse on our computers. What we need instead is to be able to synthesize that information and sort of say, aha, this information means that connection. And that's how we go forward on that. Right, we watched televisions as we were growing up before we had these LEDs and LCDs, which also are quantum devices at their core. But the first televisions, cathode ray tubes, they were indeed designed to speed up electrons or make electricity go, have lots of energy. And voila, the development of that technology let us watch the Olympics from halfway around the world. Things like that. Yeah.
it is amazing. Now I want to get back to something that we talked about earlier, and you say, scientists don't have to be these, rigid people that never have any humor. And again, this is a new piece of information for me that also is insightful, I think. You talk about Murray Gell-Mann, and he came up with the name from quarks from Finnegan's Wake, from three
That's
quarks
right.
from Buster Mark. I had no idea that's where that came from.
Yeah, isn't that funny? I when I learned it too, I was blown away. I thought it was hilarious. And Murray Gell-Mann himself, he lived quite a colorful life. He was a professor at the California Institute of Technology, and Caltech, of course, is in Pasadena, right near Hollywood. And he, surprisingly perhaps, attended all kinds of the parties from the rich and famous. He went to the Oscars. He was on the red carpet, and he was just a life of the party. People loved having him around, even though he was this sort of short old man who was a physicist, because he was just fun, and that physicist in him never stopped him from being enjoyable and enjoyed by all of his friends who were in Hollywood.
I'm also wondering if that inspired some of the later people who named things. You wouldn't expect the six quarks of the standard model to have up and down, top and bottom, charm and strange. You would have thought they'd been A, B, C, D or something.
That's exactly right. When Murray Gell-Mann knew that there was a pair up and down, but the third one, he didn't know how it connected with the up-down pair, so he just called it charm. And so from there, other folks said, yes, let's call the next one strange. And then they called the next ones truth and beauty.
Yeah.
But of course, then there was some wish to rein in that
Mhm.
creativity. I guess physicists at the time really wanted to convey at least some scientific information, not just A, B, C, D, E, F, but
Mm.
since there was up and down quarks, let's change truth and beauty, which we can still refer to them if we
Mm.
wish, but because the same letters, top and bottom. So
Yeah.
there's this kind of pairing. Yeah, it is funny that way. We are that way, scientists.
And then from there, this is a thread that came through me as I was reading the book is about supersymmetry, where you got lepton squarks gluing on neutrinos. It
That's
sounds
right.
like an old Italian law firm to me, but
Yeah, I agree. The pursuit of science really is reflected in part in these names in the sense that we like what we do. It's a fun thing to do. And when I wrote this book, I hoped to be able to convey that kind of fun as well. And you picked up on that. We're really thinking about the universe and the cosmos, or even the world around us and how it works. But at the most fundamental scales, we're humans. And we are exploring in a way that makes us think that it's cool. Science is always best and always communicated best too, when it's clear and fun and cool.
I have to say that when I was telling my wife about this, and she says, "Well, make sure you ask him about string theory." And
Mm,
I said, he probably won't mention. Sure. As soon as I got to the end of the book, there it was. So you covered all the bases. So yeah. Do tell us a couple of things I want to think people in the popular mind have caught on and need maybe more background on. One of those is spooky action at a distance.
yes. We call that quantum entanglement now in formal terms.
Mhm.
But Einstein did indeed call it spooky action at a distance because back when he was doing his research decades ago, there was no sense that it was possible to have something interact with something else far away if there wasn't some sort of exchange of energy.
Mhm.
Uh, Spooky action at a distance, this quantum entanglement thing, is basically trying to suggest that if you have two entangled particles in this quantum entanglement thing and spread them far apart, as soon as one thing happened to one of them, it would happen instantaneously to the other one, which would suggest that there was some action at a distance where there was nothing happening. So that insight led actually to our modern understanding after many decades of research, where we realized that these two particles, when they're quantum entangled and moved apart, they aren't two particles. They're actually the same particle stretched out a little bit. Okay, but the stretching isn't the kind we think of like a rubber band where there's like a space-time kind of stretch where energy is exchanged between them. Instead, they've just become a particle that happens to have two pieces, one piece of which is far away from the other. And so that's why when something happens to one of them, it happens to the other simultaneously. It's not a matter of spooky action, but it's a matter of the nature of what a quantum entangled particle or a pair of quantum entangled particles actually are.
And I know as a big time reader of science fiction that has been seized upon as the way to have instantaneous communication
Yes.
do something here, it affects it over there, so you don't have to worry about the speed of light and the fact that you're thousands of light years away and the other planet. You just boom, there you have the chasuble, it connects you instantly.
Oh, I
Uh,
love those.
Hasn't happened yet, and it, but it, at least theoretically, there's some kind of exchange going on that perhaps is measurable that'd be helpful.
Right, it would be. The thing that prevents that kind of instantaneous communication along those lines is primarily this phenomenon called quantum coherence. In other words, for those particles to remain entangled, they must remain coherent. So if you take two particles that are entangled and start separating them, how long or how far apart can you bring them before they lose their coherence and sort of just dissipate, right? Right now, the furthest we've been able to send signals and keep them, say, reasonably well coherent is about 100 miles or so, right? And if you think about the speed of light being almost 200,000 miles per second, that means that we've only been able to keep these particles coherent with one another for a tiny fraction of a second, right? So we need to keep them coherent for much longer, hours, days, or even years in order to do this kind of instantaneous communication, because you've got to make them, then separate them, and then do something to one piece, then the other piece can react. So it's not an easy task, but yes, it's fun to think about, isn't it? It's no accident, I think, that movies have been talking about the quantum realm and things that are just unknown because there are so many neat things that we only have the tiniest glimpse of. And they're fun to think about because if you can imagine something, an application that we can't think of right now, we can start trying to figure out whether we can do it. Right now, though, we're far away from that technology.
We are indeed, but at least it's entered the popular mind. You know how scientific discoveries have this promulgation delay, a lapse between the time that it's put in a peer-reviewed journal and the time that it's on the funny pages.
Sure do.
And we are now getting to the point where we have Spider-Man in across the multiverse.
Yes.
And so the concept is out there, and I think for some people it's comforting to know that everything that possibly happened has happened or will happen,
Mhm.
because sometimes we think, I wonder if I had done this, what would have happened differently? It
Yeah.
would be nice to meet the guy that happened to and see what happened to them.
I agree. Yes, the many worlds interpretation of quantum mechanics, as it is referred to, right, does indeed suggest that every time there is a quantum process, a bifurcation of what could happen and what does happen, there is actually a whole nother timeline, whole nother universe, we could call it, that's created at that moment. And so indeed, there might not be an infinite number, but there may be a very, very, very large number of things that have happened, that could have happened, that will happen, and so forth. And the extent of that is, like you said, to some people, very comforting.
Yeah.
Uh, and to others, it's sort of a way of thinking, wow, how can I take advantage of this in storytelling? What does this create in terms of the imagination of the things that I can wonder about? And I think that's really true. Yeah.
I just as a matter of pure cultural interest, uh, I believe the first time that came up in comic books
Hmm.
was in the early 1960s when DC Comics decided they were going to take their Justice League of America and visit the Justice Society of America, something they had
Yes.
created back in the 40s. So they gave Earth 1 and Earth 2 that lets them exhibit them both. So again, for those,
Absolutely right. That
it,
was a wonderful story, actually.
yeah,
The fact that the Justice Society of America existed, but then was replaced decades later by the Justice League in DC Comics. Then they put them together, and that spawned everything, right? Marvel Comics later on wound up creating something called Counter Earth, where they claim to have found another Earth somewhere else in the solar system, like exactly opposite from us. And so if we could never see it. But then, as astronomy advanced and we could see the other side of the sun from us, they moved to the same way that DC did to these alternate universes or parallel Earths and things like that. And so now we have all kinds of parallel Earths and the Spider Verse and all of its versions, as you describe. I agree. It's just a fun thing to think about, right?
it is indeed right. I'm wandering away from the actual science to do the fun stuff here, but I do want to get back to the science. as well. I think one of the things I really appreciate is the way you find examples of real world stuff that we can relate to. You talk about, and I'm not sure exactly where it is, but it's a difference in energy levels, and you talk about stair steps.
Yes,
Tell
that's
them that
right.
story. Yeah.
Sure. In our atoms and molecules, the electrons, as they move back and forth, can only move from one step to another as determined by the quantum structures of these tiny systems. So you can't just have something that emits a photon or produces an electron jump at any energy. It can only be the ones that are allowed. And so it is very much like us going up and down a staircase. We can stand on the first stair or the second stair, but we can't stand on the 2.5 stair, right? Or the 2.256789245 stair. There's either only two or three. So we can move back and forth between two and three and briefly or momentarily occupy a certain amount of energy. But when we, in the end, look at ourselves, when we've settled on something that actually is observable, we're either in two or three. That kind of discretization of energy on the quantum level leads to all kinds of important things that we do that allow us to see things. Neon lights, for example, give off light at specific wavelengths, specifically because of that reason. That's just one of the many, many examples that the stair steps analogy can help us understand what's going on the quantum level.
And by the way, again, wandering off topic, you should ever come to the Dalles, Oregon, where I hang out. We have the
Uh,
National Neon Sign Museum here, which
oh,
includes
wow!
the very first tube, the very first generating tube that generated neon. They have the actual original from the patent. So,
Fantastic.
yeah, so come on by
Okay,
sometime, we'll talk. Um,
be a pleasure.
back back to the science. This is target. I'm trying to get the audience for this is kind of a
Mhm.
mixture out there. What did you foresee this book is written for?
Oh, great question. I wanted everybody who was just curious about quantum physics to be able to pick up this book and learn something from it. I As you know, I do research in astrophysics, right? In galaxies and supermassive black holes and so forth. I'm a daily user of quantum physics, but I don't do research in sort of the weeds, the deep parts of quantum physics. So I find it useful in my own mind to think of quantum physics as a tool, and having a manual for a toolbox or a handbook is sort of the way that I would want other people to feel too. They use quantum devices every day. We are all surrounded by quantum physics in our daily lives, but we don't have to think deeply about the outstanding questions of quantum physics in order to know how to use it, in order to be sort of comfortable with it. So if you have a lot of science background or if you have no science background, all that matters is that you have some curiosity. And so the book is not dumbed down. It's not at all, made so simple that it's boring. But instead, it tells things in a language that is sort of not jargony, that is not deep. And if you want to start somewhere, you can look at it, you can get very deep concepts right away, or you can just sort of learn the top part and say, oh, that's kind of cool. And there's so much out there in the world that you can learn more about yourself. Go and study and examine, send email to a quantum physicist. There's lots and lots of ways to go. And this is our first step. Sits on your coffee table or your bookshelf. And if you're curious about something, just take a look.
Well, I love the fact that you've set this up as kind of a Socratic method where you're taking both the teacher and the student's part because you're asking the questions and you're answering it, and they follow a logical progression that's very, very clear so that you can start from here and keep going. And uh, how long did it take you to put this together?
Oh, well, first of all, thank you so much for saying that this works. It was indeed my hope to do that Socratic method and to have that progression and have people be able to think about it along that way. So if you sensed that, then I did my job. Yay. But how long it took? Wow. You could say that it took me my entire life to
Mhm.
do this, right? Specifically writing the book itself took about a year.
Mm.
of time that came through all the other work that I'm doing in my research work and in my professorial work, right? And so it was a lot of effort. But really, a lot of this material is has been brewing or has built up in my life over decades as I've been doing the sciences, as I was a student myself, and as I've done some other reading, simply because I experienced it and sort of filed it away. And even when writing the handy astronomy answered book and the handy physics answered book, I already used some of those concepts to explain those concepts. But then the concentrated idea of looking at quantum physics really arose over the past couple of years because it was time, right? Things are coming in now that we see the connections now. It's not just as subtle as it used to be. The sun is shining. That's quantum physics. But we didn't really understand that. But now we're thinking of using nuclear fusion as a way to generate energy for us. And now then we have to understand the quantum effects inside the sun that allow nuclear fusion to happen. And maybe it'll affect our daily lives. So this past year, couple years or so, was really the time to put this all on paper and assemble it into a single volume.
Wow. So I have to ask because science will not stand still. Um,
Yes.
what has happened since then that you thought, dang, I wish I'd had that in the book?
Great questions. In fact, yes, when I was writing this book, I already knew there were things that were going past me. And so I called and talked with and emailed with a number of quantum physics specialists that are really at the cutting edge. And I learned so much from them during that year that I was working on this book. The thing that has been moving so fast, which I wish I could put more in, is quantum computing.
Mm.
Quantum computers, I'm only barely starting to understand myself. But it is an area that is expanding so quickly, and it's ties in the things that we're talking about, like spooky action at distance, right? The quantum entanglement issues, quantum teleportation, which is not beaming me up, Scotty, but the ability to keep a coherent signal between quantum entanglement, quantum entangled particles, things like that. Um, the quantum computing is assembling the technology now where we may be able to increase our ability to make certain computations by factors of hundreds or thousands. Uh, you don't want to use it to like do your calculator problems like 2 plus 2 equals 4 or anything like that. But these quantum computers are literally taking advantage of things that happen within fractions of a second before they even give information to the next piece of circuitry or logic that will get us to actual giving an answer. And that stuff is well beyond me right now, but I'm learning. I'm trying.
Well, you also mentioned at some point, I probably can't find the exact in my 27 pages of notes from this, where you talk about it. But at one point, toward the end of the book, you do talk about quantum computing, and you mentioned that the very first time they only had 20 or 30 of things, and now they're up to the tens of thousands of things. So
Right.
it's going to progress like crazy. It'll snowball.
That's right. This is the qubits, which are the quantum bits that are right now mostly in the double digits, but starting to go into the triple digits and so forth, and getting into thousands of qubits per computer, right? Those are really advancing quickly. And the thing about it is, unlike our regular classical computing, where an electron is an electron, right? It's a piece of electricity that goes back and forth. And it's just a matter of how many electrons you're using to produce your signals that you're moving forward through your computer. With qubits, there are many different ways to entangle and create qubits. There are qubits that you can do with pieces of light, such as photons. There are qubits you can do using atoms and molecules. You can do them using ions. And then even if you use these different things, you can do them in different ways. You can trap the ions, for example, or you can put them on a lattice. They're just right at the edge of so many different technologies that we haven't settled on the right answer. In some cases, you can do lots with a few qubits. Other cases, you can do lots with a lot of qubits, but it's very limited in what you do. So these ideas called, for example, quantum capacities, or the ability of a quantum computer to do things is not just measured by how many qubits anymore. It's measured by how you use those qubits and the kinds of circuitry and the logic that are involved. It's way, like I said, way fun and way complicated and right at the early times. You can imagine like when people are just first starting to build railroad cars or automobiles, and there was every variety, right? And eventually we've settled down over the decades into a specific kind of structure that seems to work well for most people. But right now it's just really, really open and a neat area of study.
I think one of the things that was most intriguing to me about it was in a standard computer, it's either a one or a zero, it's on or off. It's, bifurcated, as it were. And here, the qubits are an indeterminate value between zero and one until you collapse it down to, and that to me gives you so much more flexibility long term.
Yes, you're exactly right. We can't do any calculations between the 0 and the 1 being read in a classical computer. But if you can do calculations before it gets read as 0 or 1, you you can increase the speed of your calculations by sometimes hundreds or thousands of times. So the qubit, the quantum computer, is indeed designed to say, okay, we're going to give this qubit something to do before it becomes a 0 or 1 on the other side. And if it does it in that tiny, tiny fraction of a second before it becomes read and collapsed as a 0 or 1, then we have just increased our computing power a huge amount.
Well, there goes the artificial intelligence. I will be all working for them someday.
Well, the artificial intelligence, remember, is just a reflection of our natural intelligence. We've created it to do things in ways we think our brain works. But if our brains, which are each one of ours, many, many times more complicated than the entire internet exists today, right? What's going on in there? There's the natural intelligence have some sort of quantum properties in it that will always exceed the artificial intelligence that we try to create? Or will we be able to build technology that will exceed our abilities? I mean, think about it. We built cars so that cars can go faster than humans, right? That's okay. We use the cars so that we can travel long distances quickly. But they go faster than we do as long as we're, under control. Maybe a computer in the future with artificial intelligence will do the same thing, be able to do things faster than us, but it's still our tools. It's still our abilities to be involved with them. And that will help us travel maybe to the stars.
And as long as they build them with the Asimov's three laws in it, and then we're all good about that.
Absolutely right. We have to control our technology too. You don't just start a car and then walk away from it and let it go down the street, right? We can't do that with computers either. Otherwise, we're going to get ourselves in trouble.
Well, I have to ask this because this was so entertaining. When is Son of this is coming out?
What? Son of quantum physics?
Yes. I,
Wow.
I mean, I could see this as being a series that you're doing. I mean, you've done it in various disciplines so far, but this one is advancing so fast. I can see in 3 to 4 years, you're going to have a whole new book out here.
I think you're right. I think it would be really fun to revisit this in just a few years. We don't have to wait very long, and there will be all kinds of new stuff. I think the challenge will be for me as an author to make sure that I don't get lost in the jargon, get so deep in that those of us who aren't experts, including me, wind up not being able to see the fun and the coolness and the beauty and the joy of it. That's what I will always be thinking about as I'm thinking about the next version of the son of, I guess, as you put it, the handy quantum physics answer book. It's how can I be sure that I understand it in my own head in a way that I can communicate it to others so that it's still fun and still neat.
That is so fantastic. Well, let me say from a person that reads a lot of books, and you're 858 author interview, I think. Um, this you did it. You got this job done.
Oh,
At
thank
least
you.
for some of us out there who really, really like this stuff, You will, if you have any the slightest inclination and you're listening to this, go out and buy multiple copies and give it to all your friends because they will appreciate it.
Thank you so much, Roger. I really appreciate that.
All right. Our guest today has been the inimitable Charles Liu. The Handy Quantum Physics Answer Book is the book wherever books are sold. Grab yourself some copies today. Thanks so much for being with us today.
Thank you. Thank you for having me.